Hello, and welcome back to Homework Help for Math 2. Today we're going to be looking at Unit 4, More Functions, More Features. Lesson 5, Flipped Out. Starting with the Ready section. Directions here say solve each equation for y. First assigned problem was number 3. So for number 3, we're given an equation, x over 25 plus y over 75 equals 1. We want to get this y by itself. So our goal is to get an equation that looks like y equals something. And then as long as the y is by itself and as long as the something is simplified, we're basically done. So I want to get y by itself. And as of right now, there are essentially two things that are preventing y from being by itself. There's the x over 25 that's getting added to the y, and then there's this 75 that's in the denominator below the y, which means it's being divided into the y. And I got to sort of deal with both of those things. The order in which you do this, it turns out it doesn't matter. You can either deal with the x over 25 first, or you can deal with the 75 first. I'm going to deal with the 75 first. And the reason is because, as it turns out, if you deal with the 75 first, all of your fractions go away, which is kind of nice. Again, if you deal with the x over 25, it's not a problem. You'll still get the same final answer. But I'm going to deal with the 75 first. And the way that we're going to deal with that is the 75 is being divided, right? So it's y divided by 75. So if I want to undo that, I'm going to do the inverse of division, which is multiplication. So I'm going to take my entire equation here, okay, the left and the right, and I'm going to multiply by 75, right? I'm allowed to do this. I am allowed to take an equation and I can multiply by a scalar, in this case 75, and as long as I do it to both sides, that's fine. So what's going to happen here is this 75 is going to get distributed to essentially all three terms inside my equation. It's going to get distributed to the x over 25, the y over 75, and the 1. So just to make sure that this is abundantly clear, this step might not be necessary, but I'm going to include it anyway. The 75 is just going to go into the numerator of all these fractions. So when I take 75 and I multiply by x over 25, it becomes 75 x over 25, right? I could just sort of slap the 75 into the numerator, plus, again, just put the 75 in the numerator, so 75y over 75. And then on the right-hand side, it's just 1, which means it's just 1 times 75. Right? So my first term here, 75x over 25, well, 75 divided by 25 is 3. All right, so that simplifies to 3, and my x is still there. Then I have 75y over 75. Well, my 75s are going to cancel, which is exactly why I'm doing this. That shouldn't be a surprise. So I end up getting y. And then, of course, 1 times 75 is 75. All right. So now, in order to get y by itself, the only other thing I have to do here is I have to deal with what is now the 3x. It used to be the x over 25. Now it's 3x. And it's being added to y. So if I want to undo addition, I want to subtract. So I'm going to subtract 3x, okay, which cancels. But because I did it to the left, I have to also do it to the right. I can't just randomly just subtract something from the left without also subtracting that same thing from the right-hand side of the equal sign. So when I look at my equation now, the only thing that's remaining on the left-hand side is y. And that is what we're trying to do here. That's our goal. So we're almost done. And what I have is I have 75 minus 3x. Now, if you put 75 minus 3x, that is correct, and that's fine. Nothing really wrong with that answer. If I were answering this question, well, I guess I am answering this question. If I was completing this assignment, The way that I would write this is actually I would write y equals, and sort of it's a quasi-mathematical convention to if you have a term with a variable and a term that's a constant, it's common to see the term with the variable first. It's still negative because you're subtracting, so it's negative 3x plus 75. I just sort of changed my order. Both of these are obviously correct. I think that this version is just better because it resembles slope-intercept form. But again, if you put y equals 75 minus 3x, it's certainly not wrong. And I think for the context of this assignment, it's fine. Question 4. Again, our goal is y equals something. So we get y by itself. We simplify the something, and we're good to go. So for number 4, this step is not strictly necessary. This might just be a me thing. But when I'm trying to isolate, in this case, y, I want y to be on the left-hand side. And this, again, this maybe you're not like this, in which case, congratulations. I'm actually just going to, step 0 here is I'm just going to flip my equation, which I'm certainly allowed to do. Just because I want my target thing to be on the left so that I get like y equals something. So just a real quick sort of introductory step. To get y by itself, I have to deal with the 9 and I have to deal with the 6. And yeah, you're going to want to deal with the 6 first. I guess technically you could deal with the 9 first, but it's way more work than is necessary. So it's going to make your life a lot easier if you deal with the 6 first. So that 6 is being divided, and I want to get rid of it. So I want to use the inverse operation, and the inverse operation of division is multiplication. So I can take my entire equation, and I can multiply by 6. And what's going to happen here is that 6 is going to get distributed to each term on the left and on the right. On the left, notice that the entire term, not just the y, but the y plus 9, the entire thing is being divided by 6, not just y. So when I distribute that 6 to the left-hand side here, the 6's are going to cancel, and I'm going to be left with just y plus 9. Because, again, the 6 is in the denominator of the entire left-hand side. It's not just the y. So again, that 6 is going to cancel with the 6 that's in the denominator, and the left-hand side just becomes y plus 9. And then I have to also do the same thing on the right-hand side. I can't just, randomly get rid of a 6 on the left without doing anything on the right. So on the right, it's still multiplication. It's going to be x times 6, which is just 6x. And we're almost done because the only thing preventing y from being by itself right now is that plus 9. I want to get rid of it, and I'm adding 9. So if I want to get rid of it, I use the inverse operation. The inverse operation of addition is subtraction. So I subtract 9. And by subtracting 9, that cancels, and I'm left with just y. I have to, whatever I do to the left, I have to do to the right. So I have minus 9. So I get y equals 6x minus 9. And although you could technically write this as negative 9 plus 6, that would definitely be a kind of an unusual way of expressing that. Again, it wouldn't be wrong, but if you can express something as in slope-intercept form, like why not do it, I guess? So yeah, so y equals 6x minus 9. Question 6. So question 6, we're given an equation, 3y equals 18x minus 3xy. And this question is a little, I don't want to say tricky, but it's got a couple of twists and turns, I guess. So as always, our goal is to get y equals something. So if y is by itself and the something, whatever the something is, if the something is simplified, we're good to go. And there's a couple things going on with this problem. First of all, and this is probably, if you didn't know what to do with this problem, there's a decent chance that the thing that might have tripped you up here is that we have like quote two y's. There's a 3y on the left, and there's a 3xy on the right. And again, our goal is to just have a single y, and for that y to equal something. And also, to be clear, you cannot have a y uh, on the right-hand side as well, right? Like that's no good, right? So it can't be y equals and then something else in terms of y. Like no, the only y in our answer has to be the single y on the left-hand side, and our right-hand side can't have a y in it. So that's one thing that we're going to have to deal with. The other thing that, if I'm being honest, I actually didn't catch this right away when I was doing this problem. The other thing is that in this equation, and this actually has nothing to do with isolating y. This is actually just the nature of this equation as it's written. Notice that we have a 3, an 18, and a 3. And obviously those are all they're all constants, they're all scalars. And before we do really anything else, there's actually nothing preventing us from the very beginning of this problem. There is nothing preventing us from actually getting rid of a factor of 3 from all of these terms. And this isn't really, I mean, we're going to have to do this eventually, but even if we were not isolating y, even if we were doing something else with this equation, we would be able to do this because all three of these terms here have a factor of 3, which is like not necessary. We can get rid of it. So that's actually a good first step here, which I didn't catch the first time I was doing this problem. So if we take all of our terms here and divide by 3, well, 3y divided by 3 is y, equals 18x divided by 3 is 6x, and then minus 3xy divided by 3 is simply xy. And again, if we did not do that step first, it's fine, but we would have to do that step eventually, right? Whether we do it now or we do it at the end of the problem, we're going to have to eventually deal with the fact that there's this common factor of 3 that we don't really need, and so we want to get rid of it. All right, so we took care of that. So now we have to sort of deal with the fact that we've got these like quote unquote two different y's. Like they're not different, but we have to sort of just get them down to one y. So if you're not sure what to do here, just recognize that because we want y to be on the left, even if you're not sure exactly what to do, you might think, well, we have to bring this xy over to the left, right? It can't stay on the right, so we have to bring it over. So let's go ahead and add xy and add xy and just sort of like see what happens. So now the xy term on the right is going to go away, and what I end up getting is, I guess the order that you write this doesn't really matter, but I'm going to do the xy first. So we're going to have xy plus y equals 6x. This is better, like we're making progress, because now at the very least, at least now there's no more y's on the right hand side, right? So we're obviously not done this problem, but we are actually making progress because now at least the y's are on the same side of the equal sign, which is going to be necessary in order for us to do this problem. Again, our goal is to get y equals, and we're going to have to eventually deal with that x, but before we deal with the x, we have to deal with the fact that we have like these two different terms that have y in them. When you have a situation like this and you're trying to get y by itself, the way that we can go about this is we can recognize that because both of these terms, both xy and y, because they both have a y in them, it means that my GCF here is y. My greatest common factor of those two terms is y. I can pull out a y from both of them. I can factor it out, right? Our good friend factoring has just returned. So if I factor out a y from both of those terms, here's what I get. My y comes out in front, and then, as always, when you're factoring, that introduces a set of parentheses. When I factor out a y from xy, what's left over? Well, that's x. That's relatively straightforward to see. Plus, now you have to be careful here. We have a y, and we're factoring out a y. If you were to say plus 0 here, that is incorrect. Okay? It's not that there's nothing left over. It's that you have a factor of 1 left over. That 1 is like a placeholder because, y times 1 is y. And so if you divide out a y, you're just left with 1. And another way to see this, if that was confusing, is to just recognize that if we wanted to go backwards and distribute, you need the 1 there in order to get that y term. If there's nothing there, then you only have xy, and that's not what we started with, right? So you should be able to go in both directions here. So I factor out a y, and I'm left with x plus 1. The right-hand side of my equal sign, nothing has changed in that step that we just did. And what's nice about the factoring thing is that now I have y times something, right? The something is inside the parentheses. It's a binomial. So if I want to get rid of that, again, it's y times something. So if I want to undo multiplication, I divide. Now the thing that I'm going to divide by is the entire factor inside the parentheses, which is x plus 1. All right. You can put that in parentheses if you want. It doesn't really matter for this step. And what's going to happen is on the left-hand side, it's going to go away. And I'm left with just y, which is our ultimate goal here, right? We want to get y by itself, and we just did. We just got y by itself. So now all we have to do is what's on the right-hand side. And I'm going to erase the cross off because we have to still deal with it on the right-hand side. So on the right-hand side, we have 6x divided by x plus 1. I can't really simplify that, so I'm just going to leave it like that. I'm going to leave it as 6x over. Now, in your final answer, you don't need the parentheses, so don't include them in your final answer. And you're left with just 6x over x plus 1. And that is going to be our final answer for 6 because we've isolated y. And the term on the right is as simplified as we can reasonably make it. Moving on to the set section. Directions here say, create the inverse function for each of the functions provided. Represent the inverse in the same way the original function is given. So, if we're given a graph, then provide a graph. If we're given a table, then provide a table. If we're given ordered pairs, provide ordered pairs. All right, so number 7. Number 7 says, write the inverse function for the table of values. All right, so we have a table, input and output, and the directions here are to provide a similar table, right, for the inverse function. The inverse function has its own input, which again we're going to call x in this case, and then the output is going to be represented. If our output of the original function is g of x, then the output of our inverse function is g inverse of x. And just as a reminder, this -1 is not really an exponent. This is one of those situations in math where like the symbol kind of means a couple different things, which is not great, but we just have to sort of deal with it. So that is not actually, it's not saying g to the negative first. It's just g inverse is how you would say that in this context. So, so 7's interesting. 7 is one of those questions, and I don't know if anyone has had this experience. 7 is one of those questions where if you know what to do, it is very easy. And I hate using that word easy because I know people are in a lot of different places mathematically, and that's totally fine. That's why we're at school and we're always learning and all that good stuff. So, but if you know what to do, this is a very easy problem. Now, if you don't know what to do, then you're in the right place, and thanks for watching this video. But you're going to see that once you see the answer here, you're going to be like, really? Is that it? So with this question, we have a representation of a function. We start with a table that's filled in, g of x. And what this table is saying is, when your input into the function is negative 10, the result or your output is negative 2. You plug in a negative 6, you get a negative 1. You plug in a negative 2, you get a 0. You plug in a 2, you get a 1. You plug in a 6, and you get a 2. Okay? That's what that first table is saying. The second table, the table that we're going to fill in, we're told is the inverse function of the function that we're given. It is g inverse of x. And the whole idea behind an inverse function is that it undoes the original function. Okay? So with a function, you plug in x and you get, let's say, y. With an inverse function, what the way it works is you take the output from your original function. You take the result, okay? On a graph, it's the y-axis, right? You take the result of the original function, and that becomes your input into the inverse function, okay? You're taking the previous result, and now you're starting with that. You plug that into the inverse function, and then the output of the inverse function is your original input that you started with. You undo whatever the function did. Maybe that's confusing, maybe that's not. Let's take a look and see what this looks like in a table. So, like I said, the first column here says you plug in a negative 10, you get a negative 2. With an inverse function, that means, like if you want the inverse function of your original function, it means that if you take your first output, which was a negative 2, okay, this, get rid of all this. So this number is this number, all right? You take your original result, your output, you plug it into the inverse, and your output of the inverse function is going to be whatever you started with. It's going to be the input that resulted in the original output. So this number is this number. So this is how inverse functions work. It's almost like you start with a negative 10, and then when all's said and done, well, now you're back at the same negative 10 that you started with, right? You plugged in a negative 10, you got a negative 2, then you took another function, you plugged in a negative 2, and it actually turns out that you're back where you started with the negative 10. Second column. Second column in the original function says you plug in a negative 6 into your original function, and you get a negative 1. The inverse function for g of x, so g inverse of x, means that, well, all right, if you take a negative 1, if you take the thing that you ended with, you're going to get the thing that you started with. Your input and your output just flip. All right, I think I've made my point. The rest of this table is going to be super easy to fill in. If you plug in a negative 2 and you get a 0, in the inverse, it means that when you plug in a 0, you should get a negative 2. The original function, you plug in a 2, you get a 1. That means that the inverse, if you plug in a 1, you should get a 2. The original function, when you plug in a 6, you should get a 2. That means that when you plug in a 2, your result, you should get your original input of 6. And that is my table. Question 8. For question 8, 8 says, write the inverse function for f of x. And this time, we're not given, I guess, a table of values. I mean, we kind of are. It just looks different. We're not really given a table of values. What we're given this time is we're given a whole bunch of coordinate pairs. Right? We're saying that in our original function, f of x, if you plug in a negative 13, that's your x value, that's your input, that's your independent variable, it's going to spit out a 5. That's going to be your y out. That's going to be your y coordinate. It's going to be your dependent variable, so on and so forth. When you plug in a -9, you actually end up getting the same thing of -9. You plug in a -5, your result is -2. You plug in a -1, your result is -5, and so on and so forth. Right? With an inverse function, well, first of all, the directions said use the same format to represent the inverse function as whatever it was that you were given for your original function. So the original function was, again, expressed as a set of x, y coordinates. So we're going to do the same thing. So a set, you get one of these fancy curly brackets to start. That just implies that we're talking about a set here. And the very first coordinate pair is -13, 5. You plug in a -13 into your input, and the output is 5. With an inverse function, it means that if you take your original output, which was 5, right? That was the result of the original function. If you plug in that output and you make it your new input into your inverse function, it's going to undo whatever f of x did. So it's going to take your result and it's going to spit out the original input. So that means the first coordinate pair here is going to be 5, comma, -13. We switch the x and the y. The input becomes the output, and the output becomes the input. Just keep going. The second one says when you plug in a -9, you get a -9. Well, technically, we're going to do the same thing here. We're going to take our output, which I guess was the second -9, and it's going to produce our input, which was the first -9. Now, obviously, those are identical, so it's like doesn't really matter, but we did quote unquote switch x and y for that second one. Third one. You plug in a -5 into your original function, and the function spits out a -2. The inverse function, therefore, should take your output of -2, and when you plug that into the inverse function, the output of the inverse function is going to be the input of your original function. So you plug in a -2, you should get a -5 because it undoes whatever f of x did. Next pair. You plug in a -5, you get a -1. Next pair, you plug in a -4, you get a 0. Next pair, you plug in a 6, you get a 4. If you plug in a 10, you get a 9. If you plug in a 32, you get a 14. And then another curly close bracket, because that's a set. And that is our answer. Question 9. The function g of x is on the graph. Okay. Graph the inverse, g inverse of x, on the same set of axes. All right, so we have what appears to be a linear function. So our graph of our inverse function is also going to be linear. So the inverse of a linear function is also another different, probably different inverse function. And there's a couple different ways that we can do this. If you're not sure what to do, which presumably is why you're watching this video. If you're not sure what to do, one strategy is to just recognize that with an inverse function, ultimately what you're doing is you are swapping your input with your output. So on the coordinate plane, x is your input and y is your output, which means if you want the inverse, you just take your x's and your y's and you flip them. So one way to do this problem, this is not the only way, but one way to do this problem is to say, all right, well, what's a point on my original graph? So we can start, I guess, there with our y-intercept. Nothing wrong with that. And what's going to happen is the coordinates at that point are 0. Right? The x-coordinate of your y-intercept is always 0, because when you plug in a 0, you're on the y-axis. So pretty much by definition, when you're talking about your y-intercept, your x value is 0, which you can also see on the graph pretty easily. And then our y-coordinate is 8. All right, this is for g of x, right? So g of x gives us 0. Actually, you know what? I'll use a little bit of color here. Why not? So on the original function, g of x, one of our points is 0, 8. Right? So our y-intercept. Well, what that means is that for g inverse of x, we would expect, as just one of our points, one of the infinite number of points on this line, one of our points to flip the x and the y. That's what an inverse function does. So we would expect 8, 0 to be on our inverse graph. So we can just go ahead and plot that. It's at least something. It's some information here. So 8, 0 is right there. So that green dot is on our line. Well, there was nothing special about our y-intercept here. We could actually choose any point we want. So going back to g of x, going back to our original function, we could also choose the x-intercept. Right? That point is just as valid as like any other point. So the coordinates for that point for the x-intercept, my x coordinate at that point is 16, and then because it's the x-intercept, your y coordinate is 0. Right? Just like on the y-intercept, your x coordinate is 0. On your x-intercept, the y is 0. So that means that for our inverse function, we would expect, if we take x and y and flip it again, we would expect that to be on g inverse of x. So if we flip it, we get 0, 16, which now becomes our y-intercept. So we can plot that. 0, 16 is like right there. And we actually, if we wanted to, we could continue to do this as much as we want, right? There's lots of other points that we could choose on our original function. You know, you want to choose a point that's like intersects the boxes, so like that. I mean, this line has a slope of -1/2, so you got plenty of points to choose from. You could do that, you know, as much as you want. But I guess in the interest of time, we have 2 green points on this graph, and we know that we're going to get a linear function, which means we can actually just go ahead and connect these 2 points. Just like that. And we're done. That line that we just drew is the graph of g inverse of x. As a side note, let me get rid of all these dots there and dot there and dot there. Okay. As a side note, as I think we talked about in class, another way to think about the graph of an inverse function is that it reflects over the line y equals x. So if you take a look at the 2 graphs, the original line and the line that we just drew, those are kind of mirror images of each other across that line, across the red line. That's another way of thinking about the inverse, the graph of an inverse function, is that it flips across that line of y equals x. We don't want to include it in our answer, but that is our graph. We'll wrap up with the go section. And the directions here say, rewrite the expressions in equivalent form by using the distributive property to multiply, then combine like terms. Express the values under the square root symbol with the lowest possible value by removing perfect square factors. All right, well, maybe some of those directions, maybe some of you were actually a little confused about like what this is even saying, about like what these directions all mean. Essentially, it says we're going to use the distributive property to just distribute whatever is in front of the parentheses, or using the distributive tactics that we've seen before, and then just simplify, just clean up whatever results from that. So first assigned question was number 12. So we have the square root of 3 times the quantity of 4 plus 5 root 3. Notice that the 4 and the 5 root 3 cannot be combined. You cannot combine a rational number, which is 4, with an irrational number, which is 5 root 3. So those two things kind of have to be separate. It's similar to, if you had 4 plus 5x, you can't combine those either. The 4 and the 5x are unlike terms, and it's a very similar concept here. 4 plus 5 root 3, that's as simple as you can make what's inside the parentheses. So the direction said just apply the distributive property to this. So what we're going to do is we are going to take our root 3, and we're going just like any other application of the distributive property here, we're going to take that number and we're going to distribute it to both terms, just like you've seen before. And whenever you've used the distributive property before, and I think everyone has some experience with the distributive property, it's the same idea, same general idea. So this becomes, we have root 3 times 4. Now, the mathematical convention here is, you can actually see it in the problem. Notice that with something like 5 root 3, when you have a number like this, the first number is sort of the rational coefficient, which is 5. Then you have the irrational number, which is the square root of 3. Okay? So when we multiply the square root of 3 times 4, technically we could write this as root 3 times 4, right? Technically that is quote unquote correct, but it looks bad, all right? And the reason is because it's like super easy to like extend it a little too much, and they're like, oh, like is that 4 underneath the square root? So to avoid that problem, I know that I would run into that problem all the time because my handwriting is not great. To avoid that problem, the convention here is that you would start with the 4, then you would multiply by the square root of 3. Okay? So again, even though root 3 times 4 is technically correct, you're really going to want to write this as 4 root 3 and not root 3 times 4. All right. Plus, I have root 3 times 5 root 3. And just to clarify, that is 5 times root 3, just like our first result is 4 times root 3. So we have root 3 times 5 times root 3. Well, just on a kind of a pretty straightforward level, that means we have 5. Okay, we have 5. And then we have root 3, but we're going to multiply by another root 3. So, you could write that as like times another root 3. That would be correct. And that might not be a bad idea to write it like that. I'm going to actually use exponents here. And I'm going to say, all right, well, that's actually root 3 squared, right? Because anything times itself is squared, is that thing squared. So because we have a root 3 times root 3, I can just say that as root 3 squared. Now, what's kind of interesting about this result here, the 4 root 3, nothing really changes with that. That's kind of sitting there, kind of waiting for us to finish whatever it is that we're doing here. On the right-hand side, on the second term here, we have 5 times root 3 squared. Well, um, if you have the square root of a number, I'll do this in red. If you have the square root of a number, but you are squaring it, square root and squaring are actually inverse operations. So if you take the square root of x squared, the square root and the squared cancel and you're left with x. Okay? So the square root of x squared is x. There might be, I think I'm probably missing something here involving negatives. But let's, you know what, just to cover my bases here, let's just, like, x is positive there. Now we don't have to worry about that. So as long as x is positive, this is true. All right, so if x is a positive number, and in this case it is because it's 3, the square root of x squared is the same thing as x. Yeah, if x is a negative, you run into some problems with imaginary numbers, but we're going to just table that for right now. Possible problem with imaginary numbers. So anyway, in our second term here with the 5 times the square root of 3 squared, the square root and the squared are actually just going to go away, and we're going to be left with simply 5 times 3. Right? Because the square root went away, the squared went away, and I'm left with just 5 times 3. And 5 times 3 is, you know, obviously 15. And if I were completing this assignment, I personally would start with the rational part of my answer, which is 15, and then I would write the 4 root 3. All right, so that is how I would express our final answer. If you wrote your answer as 4 root 3 plus 15, that's fine. It's certainly not wrong. I just, you know, the convention is to start with the rational number and then end with the irrational number. But no matter how you write it, it's 15 plus 4 root 3. All right, number 13. For number 13, it's going to be pretty similar to 12, at least on a conceptual level. We are again going to take our try it again. So we're going to take our monomial, our leading term, and, you know, just like past experience with the distributive property, we are going to distribute it to everything that's inside the parentheses. We're going to multiply. So let's go ahead and do it. So I have 6 times the square root of 11 times 2. All right, so everything is getting multiplied. 6 times the square root of 11 times 2. I can multiply whatever's in this situation, the 6 and the 2 are not underneath the square root. They're rational numbers. So when I multiply, I can multiply them together. So 6 times 2 gives me 12, and then the root 11 is still there, right? So when you're multiplying, if 2 numbers are not under the square root, you can multiply them together. And if you're multiplying 2 numbers that are under a square root, you can actually also multiply those together and keep them under the square root. So we end up getting 12 root 11, which is 12 times root 11, minus. So now we have 6 times the square root of 11 times the square root of 11. Well, that is 6 times the square root of 11, and I have 2 of them. I have root 11 times root 11. So I have root 11 times itself, which is another way of saying root 11 squared, because it's root 11 times root 11. Not a whole lot I can do with the first term. That's about as simplified as I can get it, because again, 11 is prime here, so we can't simplify the square root of 11. The second term, my 6 is still kind of hanging out, and as we saw with number 12, when you have the square root of something squared, that actually simplifies to just the number itself. Your square root and your squared go away because those are inverse operations. It's just like, adding 6 and then subtracting 6, or multiplying by 2 and dividing by 2. They cancel each other out. So this is where we're at. And 6 times 11 is 66. And the way that I would express the final answer here, even though my rational number is going to be negative, I would probably still start with it. So my final answer in this case would be negative 66. That's the rational part of my answer. And then the 12 root 11 is positive, so it's going to be plus 12 root 11. And again, the only reason I changed my order here is because it's quasi-conventional to start with the rational part and then end with the irrational part. But again, if you wrote your answer as 12 root 11 minus 66, that's okay. That is not wrong. And actually, in some contexts, it might even be better. But for me, in the absence of any reason not to, I would say that the final answer for 13 is negative 66 plus 12 root 11.